Hey everybody, this first video lesson is going to be the first of 3 videos that are going to discuss ionic and covalent bonding. Before we get into bonding, it's important to ask ourselves this question: why do bonds happen anyway? You could ask the same question about humans. Why do humans bond? Why do friendships and relationships form? And the answer is the same for both humans and atoms, and the answer is stability. When humans are in a stable relationship, they're happy and they tend to be more productive. When atoms are in a stable relationship, they bond to one another and they're stable and they don't explode or react violently. Now, what defines stability for a chemical? The stability is defined by having a full valence electron shell. When atoms have full valence electron shells, they are in their most stable state. Now, the next question is, how do you know if it's a full valence electron shell? For really small atoms, as you know from the last chapter, full first energy level is full at 2 electrons. Now this only applies to a number of elements, primarily hydrogen. But there are other elements that are stable, and they're stable at a higher number of valence electrons. That number happens to be 8. All elements at the second energy level and lower are full or stable when they've achieved 8 electrons in their highest energy level. So if you're looking at electron configurations, a full second energy level has a 2s2 and a 2p6. So in other words, if you have a full s and a full p orbital, you are considered to be a stable element. And the elements on the periodic table that come like this naturally are the noble gases. They all have a full s and full p orbital, which is why they're considered the most stable elements on the periodic table. Next, we're going to talk about something called the octet rule. The octet rule is what drives bonding. All elements want 8 valence electrons, and we'll get to it by any means necessary. This means that it'll do one of 2 things. They'll either share their electrons or they'll exchange electrons. Now we define these 2 ways as different types of bonds. Sharing electrons is covalent bonding, and exchanging electrons is defined as ionic bonding. Let's talk about ionic bonding first. The first thing you need to know about ionic bonding is that it typically happens between metals and nonmetals. Metals tend to come with low numbers of valence electrons. Anywhere from 1 to 3 is usually the case. And nonmetals have high numbers of valence electrons in their highest energy level, typically between 5 and 8. So when these 2 different types of substances come in contact with one another, metals want to get rid of their electrons and nonmetals want to gain their electrons. I'll illustrate with a couple of pictures here. If you look closely at lithium here, it's got 1 valence electron, or 1 electron in its highest energy level. I've labeled it in red. Now taking a look at fluorine, it's got 9 protons and it's got 2 electrons on the first energy level and only 7 in the second energy level. So it has 1 less than 8. Now lithium is going to give its electron to fluorine, and it's going to be an advantage for both the metal and the nonmetal. And here's why. Metals achieve a full valence shell by getting rid of their valence electron, opening up the full inner energy level beneath it. For lithium's case, it opens up a full first energy level, which is full at 2. And in fluorine's case, it takes on an extra electron, which would fill up its almost full energy level, which has 7. Both the lithium and the fluorine benefited from the loss gain of electron, and now we've got 2 ions. Now the exchange isn't the ionic bond. The exchange does not actually make the ionic bond. It's what happens now that the electrons have been exchanged. An ionic bond happens between the positively charged ion, called a cation, and the negatively charged ion known as an anion. These 2 opposite charges are now going to attract one another, and the result is a positive-negative attraction, kind of like 2 magnets. And the bond is the result of the attraction of the opposite charged ions. Looking at a periodic table, you can use it as a tool to predict the charge that an ion will have when it loses or gains an electron to reach a full valence shell. It's actually quite easy and follows the trend of valence electrons along the periodic table. Looking at the first three columns of the main block of the periodic table, you've got the alkali metals, the alkaline earth metals, and then this column with boron, aluminum, and gallium. The first column all have one valence electron, or as we learned last chapter, they all end as an S1. This second group of elements, known as the alkaline earth metals, all have two valence electrons and all end as S2. And this first group of the P block end as S2P1s. All of these elements in these columns are likely to lose their electrons to become positively charged. So if you lose one electron, you become +1 charge. If you lose two electrons, you become +2 charge. And if you lose three electrons, you become +3 charge. So the pattern emerges as the plus charges get bigger as you move to the right. Now you'll see hydrogen is listed over here with the halogens, and this is just one way that this periodic table can be organized. But in fact, hydrogen is usually forming a cation with the group 1 metals. Even though it's not a metal, it's often listed over here on the top of the first group. And in this case, having hydrogen here is actually not advantageous to us. It'd be better off if we wrote hydrogen over here over the top of lithium. Because when hydrogen is an ion, it is a +1 ion like the alkali metals. Now taking a look at the anions, or the nonmetals, working our way back to the left, starting with the furthest group over, the noble gases. They have 8 valence electrons, and so their charge is not applicable. There is no charge. They will not lose or gain electrons. They are stable. But the elements directly to the left are the halogens, and they all have 7 valence electrons, and they'll just gain 1 to make a -1 charge. These elements, oxygen, sulfur, and selenium, are likely to gain 2 electrons because they have 6, gain 2 makes 8, which is why they all have a -2 charge. And nitrogen, phosphorus, and arsenic all have 5 valence electrons, and they're likely to gain 3 rather than lose the 5, because ideally it's what's easiest. They'll gain 3 to get 8. Thus, all of these elements in this column will form a -3 charge. Now, this is the time where someone asked me, what about this column here with carbon and silicon? And truthfully, these elements could lose or gain their electrons because they're 4 away from 8 by gaining or 4 away from 8 by losing. And to be truthful, they rarely make ions anyway, but if they would, you can say that they could either add or subtract 8, and they'd be plus or minus charge of 4. But, as I mentioned, truthfully, this is not likely to happen because they don't form ions. These are all nonmetals for the most part. Now with this information and this periodic trend, which is another trend of our periodic table, we can do our next activity, which is taking elements and determining their formulas based on the charges. And we'll talk about the rules on how to make ionic compounds next. So this last activity that we're going to do for this first video is make some ionic compounds. And there's a couple of things that you need to keep in mind before you've finished your ionic compound. First of all, the ionic compounds are always drawn with the metal first and the nonmetal second, or the cation first and the anion second. This is important because if you do it the wrong way, it's wrong. You always put the cation first, the anion second. The second thing you need to look for when making ionic compounds is electroneutrality. And what that means is that the charges always cancel one another out. When two ions, a positive and a negative ion, get together, they will combine in a ratio that eliminates their charges, and so that they're in the lowest common multiple of the cation and anion so that no charge occurs. Essentially, they are neutral, where the concept of electroneutrality comes from. So what's going to happen next is we're going to scroll down here and bring up a couple of examples, and we're going to work these problems out and make these ionic compounds with the proper formulas so that their charges are all balanced, or they are all electroneutral. So let's get started with the first one. Using your periodic table, identify the charge that this first combination of atoms would incur. So in other words, what charge would calcium have and what charge would sulfur have? Calcium would be a +2 and sulfur would be a -2. And since they're equal but opposite, they simply combine one of each to make the compound CaS. Like that. Now this next one has strontium and bromine. And if I look at my periodic table, strontium is in the second column, and so it has a +2 charge, and bromine has a -1 charge. What this means is if I take one of each of these ions, I'm going to have a leftover +1 charge. So essentially what I need to do is take this bromine and multiply it by 2. Two negative ones will equal 1 + 2. And if that's the case, then the molecule is SrBr2. And I put a little 2 down behind the bromine, which says that I have 2 of these atoms. So there's 2 bromines for every 1 strontium. Now this next example is another one where I've got to pay close attention to the charges. If I take a look at potassium, it's a +1 charge, and nitrogen is a -3. And once again, I got those charges from the columns over the top. I've labeled the columns, and I know what the charges are of all those elements in that column. So if I take one of each of them, I'm going to have leftover -2 charge left over, because -3 + 1 is -2. Well, basically what I need to do is multiply this potassium 3 times, because 3 + 1s will equal or is equivalent to 1 - 3 charge. And if I do that, then my substance is K3N. Now I hope you're getting the hang of it by now, but let's do this last one, which is the most difficult one of all by far. If I take a close look at the ions, the aluminum is a +3 charge, and the oxygen is a -2 charge. And essentially what I'm looking for at this point is trying to figure out what would be the lowest common multiple of +3 and -2, or just 3 and 2. And the answer is 6. So if I take the aluminum and multiply it by 2, I get 6. And if I take the oxygen and multiply it by 3, I get 6. And now I have the right amounts of aluminum and oxygen to accurately make my ionic substance. And the molecule is Al2O3. Because I have 2 + 3 charges equal to 3 - 2 charges. So this molecule is electroneutral. That takes care of this video lesson on ionic bonding and writing out ionic molecules. Thanks for listening.